Okay, welcome to section 6.1. This is the first section. This is the this section 6.1 and section 6.2 are included in module 1. So we've got a little bit left before we'll be finished with our first module. So we're gonna talk about what a radian means, and we start off by looking at the definition of radian. So let's read what we have. An angle with its vertex. Now this first sentence I will tell you is very wordy, but if you just bear with it, I'll explain what it's saying. An angle with its vertex at the center of a circle that intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. Okay, so what this is saying is that if you look at a circle that's centered at the origin, this distance, the radius of your circle from here to here, and then take this same distance and measure it as an arc along the side of your circle. So if this radius is the same as this arc length, and you then draw you draw a ray for your terminal side of your angle that intercepts at the end of that radius. This angle is 1 radian. So that's what a radian is. A radian is an angle whose ray intercepts the arc when the arc is exactly the same length as the radius of the circle. Okay, so I hope the picture makes it a little bit more clear than that sentence did. Okay, so if you've got an angle where the arc length is the same distance as the radius of the circle, then you have a radian. And we'll be converting back and forth between degrees and radians a lot, so we'll have to be really careful to make sure that our calculator is always in the correct mode anytime that we're needing those types of computations. Alright, now we know from geometry the circumference of a circle is given by the formula c equal to pi times the radius. Okay, so in this next picture I've drawn, I'm doing the same concept that I had in the first picture. I've got my radius, but what I'm trying to show here is that if we go 1 radius length, and then we go another radius length, and another radius length, and another radius length, all the way around the circle until we get back to our starting point, that's a complete rotation of the circle. And by this formula, that would be 2 pi radians. Okay, now don't just count off what I've drawn because this is arbitrary. But by our formula for circumference, if you're measuring these off in radians, where each of these arcs is the same as the radius distance here, when you go all the way around the circle, you have traveled 2 pi radians. So that means that 2 pi radians is the same thing as, if you measure this in degrees, we know that the full rotation around the circle is 360 degrees. So an angle of 360 degrees, or a complete circle, has a measure of 2 pi radians. Alright, so that's really important, especially as far as building our unit circle. So it follows that an angle of 180 degrees has a measure of pi radians, because that will be half of a circle. 180 degrees, of course, is half of 360, and pi radians will be half of 2 pi radians. So I'm going to pull out my unit circle while I'm talking about this. Alright, so let's look at the unit circle again. So you can see on here, this is our starting point. This is 0 degrees, and it's at the point order pair 1, 0. So remember, the unit circle is a circle whose radius is exactly 1. It starts from the origin, the radius is 1. And this point is order pair 1, 0. We've talked about sine and cosine for these. But if we go all the way around the circle and we come back to where we started from, we've traveled 360 degrees, but we've also traveled 2 pi radians. If we go halfway around the circle to here, we've traveled 180 degrees, which is pi radians. Alright, if we look up at up here, like let's say if we've only gone a fourth of the way around, so we're sitting up here, we know that's a 90-degree angle. It's also pi over 2 radians. So you're going to become more and more familiar with these radian measures. It's going to take a little bit of getting used to, because you're probably not used to working a lot with pi, but it will get easier. If we look at the 45-degree angle, the 45-degree angle is the same as pi over 4 radians. So as you're studying, especially this first quadrant, start paying close attention to these fractions involving pi for your radian measure. Okay, the next thing we're going to talk about is how to convert between degrees and radians. We use the following equivalences. We know that 180 degrees is equal to pi radians. So we can say that 1 degree is equal to pi over 180 radian. And we can also say that 1 radian is equal to 180 degrees over pi. Alright, so in example 1, we want to convert each degree measure to radians. So part A, I've got 45 degrees. When you do this, I think it will be helpful if you think of it in terms of dimensional analysis, where you're going to multiply by a conversion factor, and you want to be left with a radian, so you need degrees to cancel out. So in your denominator, you would put your 180 degrees. That way degrees will cancel. And in the numerator, we know that we need to have pi. Okay, so the degrees cancel. And then we can simplify. You can use your calculator. You can do, you can say 45, you can do it by hand, or you can say 45 divided by 180, and then go to math 1, enter. That would be 1/4. So that gives us 1/4 times pi, which is the same thing as pi over 4 radians. Another thing that's very important is that if you don't see a unit, it's understood to be radians. So we don't always write radians, but you'll probably know you're in radians when you see your pi symbol, more than likely. Alright, in part B, negative 270 degrees. Alright, so we're going to convert this to radians, so we'll have negative 270 degrees times, put your conversion factor, you want to put the 180 degrees in your denominator, put pi in your numerator. Alright, and then you can reduce. This is going to be a negative value. Alright, 270 over 180, and then my zeros cancel. 27 over 18 is going to be 3/2 because 9 goes into both of them. So I get 3 pi over 2. So negative 3 pi over 2 is my answer. And in part C, 249.8 degrees. So we'll do 249.8 times pi over 180, so that our degrees still cancel. This time you're going to need to use a calculator because it's not easy to reduce. So 249.8 divide by 180. Alright, we get this long decimal, and I'm not sure if they want us to leave this one as a decimal. Let me double check on that. I don't remember. Yeah, we're going to leave this one as a decimal. So I've got this 1.3877777 on forever. And then, so now I'm just going to multiply that times pi on my calculator. So second, and then little caret key over here on the side. You can't see that, but it's right here. So I went second caret to get to the pi button. It gives me 4.36 if I round that. So 4.36 radians. Okay, and that's it for that one. In example 2, we're asked to convert each radian measure into degrees. So this time you're going to say 9. So in part A, it's 9 pi over 4. We're going to set this up. This is currently in radians, but it's also got pi in the numerator. And so it makes sense to put, when you convert in the conversion factor, put pi in the denominator so that they cancel out. And you put 180 degrees in your numerator. Okay, and then you can simplify that. So you're doing 9 times 180 and divide by 4 gives you 405 degrees because pi cancels out. For part B, we're doing negative 5 pi over 6. We're going to multiply that by 180 degrees over pi. Okay, so to me these are easy because you just set it up so that whatever you don't want cancels out. This way pi will cancel. 6 goes into 180, that goes in 30 times, and then 30 times negative 5 gives me negative 150 degrees. So that one's not hard. For part C, I'm converting 4.25 radians into degrees. So I'll do 4.25 times, okay, this one doesn't have pi in it, but you know you need to have degrees left, so you're going to put pi in the denominator and 180 degrees in the numerator, and use your calculator. So 4.25 times 180, divide that by pi. That gives us 243.5 degrees. Okay, so to me, converting back and forth between radian and degrees is not that bad. All right. Next thing is the agreement on angle measurement units. If no unit of angle measure is specified, then the angle is understood to be measured in radians. So that's what we just saw in the previous example. Many times you'll suspect that it's in radians because you'll see pi in part of it in the number. But if you don't see a unit, then it's understood to be in radians. All right. Next thing we're going to talk about is arc length. So remember, arc length is like, let's go back to the unit circle. Okay, an arc, for example, might be the distance from here to here. Okay, so that's an example of an arc. We're going to talk about how to measure the length of an arc here. So the length S of the arc intercepted on a circle of radius r by a central angle of measure theta radians is given by the product of the radius and the radian measure of the angle. So that gives us this formula, S equals R times theta, where theta is in radians. It's very important. Theta must be in radians before you can use this formula. So S is your distance, R is your radius, theta is your angle, and it has to be measured in radians. All right, and I think we're ready to look at an example. Looks like my camera needs to focus, so I'll give it a second, see if it can focus. So we're finding arc length using S equal R times theta. A circle has radius 18.20 centimeters. Find the length of the arc intercepted by a central angle having each of the following measures. So in part A, we have 3 pi over 8 radians. Part B, we have 144 degrees. For part A, our angle is already given to us in radians, so we can go straight to our formula. We're going to say S equals R times theta. We were told that our radius is 18.2. So S equals 18.2 times, and our angle is 3 pi over 8. And we can multiply these using the calculator. Okay, so 18.2 times 3 pi over 8 gives me 21.44. And because my radius was a decimal, I took that to mean that I could leave my final answer as a decimal and that would be okay. And I think that's the way the book did it. Did they leave it as a decimal? Yep, they sure did. Except I made one mistake though. What unit should I be in? S is my arc length. It's not an angle. Okay, my arc length was measured in centimeters, so my units are centimeters. For part B, my angle is 144 degrees, and I'm sorry, that was my work there. In part B, my angle is 144 degrees. Before I can go to the formula, though, I have to convert this into radians. So I need to say 144 degrees times pi over 180 degrees. And see what that gives us. That gives me 2.513, and you know what? I'm not going to do this one as a decimal because it was not given to me as a decimal, so I'm going to keep it as a fraction in exact form. So I'm going to say 144 divided by 180, enter, math 1 for fraction, and enter. So I get 4/5, so that means I've got 4 pi over 5. So that's what I'm going to use for theta. And now I can go to the formula to get the arc length. S equals my radius 18.2 times my angle theta 4 pi over 5. So S equals, and then I'll multiply this. Now that I've got a decimal, I'm going to leave my answer as a decimal. So 18.2 times 4 times pi, and then enter and divide all that by 5. I get 45.74, and this was in centimeters. Okay, so that's how the arc length formula works. Now we get to use arc length formula for an application. In example 4, we're finding the distance between two cities, and I've got a little illustration over here in the margin for you. Latitude gives the measure of a central angle with vertex at Earth's center, whose initial side goes through the equator and whose terminal side goes through the given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north. And here they just remind us, or they tell us that N means north of the equator. The radius of Earth is 6,400 kilometers. Find the north-south distance between the two cities. So we've got the radius of the Earth, so this is from the center of the Earth to the Earth's surface, that's 6,400, I believe it was in kilometers. And then we've got our two angles. For 34 degrees, it was 34, I'm sorry, this is the equator, not the center of the Earth. The radius of Earth is 6,400 kilometers, and we're taking this, we're taking this from the equator. So we've got 34 degrees from the equator to Los Angeles and 40 degrees from the equator to Reno. We need to find this arc length over here from Reno to the equator. Okay, so to do this, all we need to do is, we're asked to find the north to south distance between the two cities. So what's the distance from here to here? So to find this, first we're in degrees. So to get it in degrees, what is the distance from the 40 degrees north to 34 degrees north? Well, 40 degrees minus 34 degrees would be a difference of 6 degrees. Okay, and of course we have to convert our degrees into radians. So 6 degrees times pi over 180 gives us a difference of pi over 30 radians. Okay, so pi over 30 radians is our theta. So theta equals pi over 30. Now we can go to our formula for arc length. So S equals, the radius was 6,400 times pi over 30. And we can do this calculation pretty easily. And then multiply that by pi. Okay, so we get 670.21. And that was in kilometers. So it's telling us there's a difference of 670.21 kilometers between Reno, Nevada and Los Angeles. Okay, let's look at example 5. Now we're finding a length using our formula S equal R times theta. A rope is being wound around a drum with radius 0.8725 feet. How much rope will be wound around the drum if the drum is rotated through an angle of 39.72 degrees? Okay, so we're trying to determine the arc length from here to here if it's turned at an angle of if it's rotated through an angle of 39.72. So we need to convert the 39.72 into radians. Multiply by pi over 180. See what that gives us. Okay, that's giving me 0.693244. Okay. And then to get our arc length, we're going to do S equals our radius 0.8725 times our angle theta 0.69324. So I'm just going to keep the same number on my calculator screen and just multiply that by the radius 0.8725. That's giving me 0.605 if I round it. And this unit would be in feet. Okay, so that's example 5. Example 6, and there it is if it wasn't showing up before. Alright, example 6. Finding an angle measure using S equal R times theta. Two gears are adjusted so that the smaller gear drives the larger one. If the smaller gear rotates through an angle of 225 degrees, through how many degrees will the larger gear rotate? Okay, so if we can determine the arc length of the smaller gear, then we can use that same arc length to get the number of degrees for the larger gear, because the arc length will be the same. So as this one is rotating, wherever they're touching, however far they touch here is going to be the same for the two gears. So let's use the radius that we're given. We're told that the smaller gear rotates through an angle of 225 degrees. Okay, our degrees needs to be converted into radians, so we'll convert 225 degrees times pi over 180. Let's see what that gives us. Okay, that gives me 3.92699 radians. You know what? I probably should not use a decimal there. Let me do that again. I'm going to do 225 over 180. I'll put this up here where you can see it. So I'm going to do 225 over 180. And then I'm going to, that's 1.25. If I want to convert that to a fraction, I'll go to math 1, enter. That's 5/4. So let's write this as 5 pi over 4. We want to avoid these decimal approximations until we get to the very end of the problem as much as possible. 5 pi over 4. Okay, so that is my angle in radians. Now I'm going to do my distance, or excuse me, my arc length is equal to my radius, which for the smaller gear was 2.5 centimeters. So 2.5 times 5 pi over 4. Alright, now that there's a decimal here, I'll probably leave mine as a decimal also. So my arc length gives me so we have S equals 2.5 times 5 pi over 4, and we will calculate this. 2.5 times 5 pi over, actually let's keep, I'm sorry, let me do that again. I'm not typing pi in because I want to keep it in exact form, so I'm actually going to keep pi as part of my result. So I'm going to say 2.5 times 5, and then, you probably can't see that, and then divide that by 4. So 2.5 times 5 divided by 4 gives me 3.125, and then go to math 1. So my fraction is 25/8, so that would be 25 pi over 8 for my angle, excuse me, for my arc length. Okay, so my arc length is 25 pi over 8. Now let's look at the larger gear. Okay, the arc length for the two gears is going to be the same because it's going to be the distance where the two are touching. So as this one rotates, the other one will rotate, and they will touch for whatever the arc length is. We're asked to find the number of degrees that the larger gear will rotate. So we need to do S equals R times theta, and we know that S is the 25 pi over 8. And my radius for the larger gear is 4.8 centimeters. And then I have to solve that for theta. Okay, so now that I've got the decimal, I'm going to just use decimals for this part. So I'll have 25 pi over 8, enter, and then divide my decimal by 4.8 to get theta. So 2.0453. Okay, so this is my angle in radians. I need to give it in degrees. So if I convert this into degrees, I'm going to have 2.0453 times 180 degrees over pi. Okay, so how many degrees does that give me? .0453 times 180 divided by pi, and that gives me 117.2 radians. Excuse me, degrees, I'm sorry, degrees. 117.2 degrees. Okay, does that answer make sense? Well, the larger gear had an angle of 225 degrees, and we found that our, excuse me, let me say that again. We were told that our smaller gear had rotated through an angle of 225 degrees. So a larger gear rotating at 117.2 degrees sounds fairly reasonable. Okay, so that's example 6, and I think we got one more. Example 7, we're going to find the area of a sector-shaped field. A centripivot irrigation system provides water to a sector-shaped field with measures shown in the figure. Find the area of the field. So in our sector, we've got a radius of 321 meters, and this angle rotates, it rotates at 15 degrees. So, sorry, you can't see that there. So our angle is 15 degrees. However, we know that we have to convert this into radians. So we are going to convert 15 degrees. Sorry about my paper here. I goofed up and had to start over again. We're going to convert 15 degrees to radians first. So if I multiply by pi over 180, that's going to give me an angle theta of, let's see, 15 divided by 180, and then go math 1, and you get 1/12. So that means our angle theta is pi over 12. So theta equals pi over 12. And now we can find the area of the sector. So we're going to say A equals pi r squared times theta. I'm sorry, it was 1/2, excuse me. It was 1/2 r squared theta. So our formula is 1/2 times r squared theta. Okay, so we're going to put in the pi over 12 for theta. That gives us A equals 1/2. Our radius is 321. We need to square it. And then, man, you can tell I'm getting tired now. I'm putting in an M for 2. There. Alright, and we're putting in pi over 12 for theta. Like that. Okay, and then we do these calculations, and that should give it to us. Be careful when you do your calculations. Remember, order of operations tells you to square first. So you're going to do 321 square. And that gives us this big number. And then I'm going to multiply that by pi over 2. So let's multiply that by pi. Not pi, I'm sorry, not pi over 2. 321 squared gave me 103,041. Alright, and then I'm going to multiply, I'm going to keep multiplying across the top. So multiply that by pi. I get this big number. Then I'm going to divide, well, in the denominator, this is all one fraction. You can think of this as all one fraction. So in your denominator, you have 2 times 12. So that means you're dividing all this by 2 times 12, or 24. So the number that I got in the numerator, I'm going to divide by 24. And that's giving me 13,488. So our area is equal to 13,488. Area is always measured in square units, and this one's going to be in square meters. So 13,488 square meters is the answer for example 7. And that completes section 6.1. So we're almost done with module 1. Alright, so good luck with these, and we will talk about these in class.